Hi, Kevin. This is Miha.
Hey, Michael, how you doing?
Good, how are you?
Doing good. Can you see my screen?
I can. The 641 CO induction disc relay.
Yep.
Perfect. So I'm about to walk into the meet because everything starts at 5:30. So I'll be listening in, but unfortunately I won't be able to contribute as much as I'd love to. But I'll be listening in.
Okay.
I'll be smuggling this thing in one ear.
Well, hopefully somebody can record for me. Last time I recorded, couldn't find the recording afterwards.
Yeah, so I pushed the record button, so
okay.
Should put it somewhere to SharePoint. I'll try to dig it out afterwards. Hopefully it won't go straight to my phone. We'll see. But it says it's recording. So I really appreciate you taking the time out for teach us more about these old relays, especially that they're all going out of style.
Yeah, so this is a topic that, as a protection engineer, I love protection. So it's a fun topic to discuss.
Now tell me if this is just a rumor or not. Before I hit the door here, I'm hearing that some of these major parts of the BES, they're actually going back to electromechanical relays because they're Russia proof. They're immune to Russians. Is that a real thing?
My experience, I have not seen that.
Okay.
There's just too many, if anything, you're not connecting communications to the relay and still keeping the microprocessor, because you can do that. I mean, it's unhackable if there's no communications to the relay as well, right? You put an air gap in that communications path, that it's not a problem.
Yeah. Well, until we went to AMI, I don't know, 6 years ago or so, we were completely air gapped. We had no reason to to touch the internet. But then we went to AMI and it kind of just started touching networks.
Hello, everyone.
Oh, okay. I'll let you go. Okay, I'll start listening. Thank you.
Hello.
Hi.
Let me check my invite real quick and see how many people accepted. Looks like there's only one person missing who at least accepted the meeting. So I'll give them another minute just for everyone's information. Michael is recording this meeting, so unfortunately I can't. I'm using my work laptop for this particular presentation. So hopefully there's no issues. We can get it posted and share it with everybody. So hope everybody's okay with being recorded.
Sure.
Yep, I'm fine.
Wait just another minute and then they'll get started. It's hard to believe that the 8 weeks has gone by so fast. Well, maybe for me it's been fast. Maybe it's been a little bit longer for you guys. For me, it seemed like it's gone by fast.
No, that was quick, Kevin.
So I think it all depends on, if you're having to do the coursework or not.
Yeah, it was pretty good work, but I think we were really busy. That's why I think it passed by real quick.
Yeah, definitely will keep you busy. Okay, well, I'll go ahead and get started, and he can join if he gets a chance, and if not, he can hopefully have a recording of this. So the last time we met last Saturday, there was some, we talked about what the meeting was about, but then there was some, interest in talking about electromechanical relays. So I kind of took a couple different presentations, put them together. There's probably more detail in here than what you guys wanted, but the point was to kind of go through this and then, kind of open discussion, answer questions. This is more, I look at this as more of a discussion than anything. So feel free to, on any slide, just, interrupt me and say, hey, Kevin, can you, explain this, or, back up. Happy to do so. So hopefully most of you are familiar, and I know at least from, the previous week that you'll recognize a couple of these numbers. I'll say these are some of the most common numbers that you're going to run across, and they're IEEE. So they're, Institute of Electrical and Electronic Engineer device designations. The nice thing about this is it keeps all protection engineers on the same page, or, substation engineer. Everybody looking at substation drawings, we're all on the same page. If I look at a 50, I know that that's an instantaneous overcurrent. If I look at a 51, I know that's a time delayed overcurrent. 52 is a breaker. Breakers have A and B contacts. 79 for a recloser. 81, there was some discussion of frequency elements. Those are, 81s. I know Michael had brought up, a differential relay, that's an 87. So a lot of these are the, pretty common numbers. So, induction-based relays, and that's what the CO class of relays are an induction disk relay. And they're used in lots of different things. So they're used from anything in distribution feeder, inline reclosers, transformer overcurrent protection. They can be used for bus differentials. I'll say a caveat there is, I think there was some discussion of the, why having a restraint quantity was good. You want versus just a straight 51B. They can be used in transmission for phase and ground, especially if it's a radial line. And then also to back up some of the generator protection. So here's a pretty simple one line. So it's coming off a 115 kV source. We come here, 20 MVA transformer. You can see, this is, since it's a one line, it shows that, hey, there's 3 CO9 relays doing 50-51 elements here. On the low side of the transformer, there's a single neutral, so 51N. It happens to be a CO11. Both of them, if they operate, they get the 86 relay that then goes and opens the circuit switcher. Then we've got our feeders. Then we've got, CO11s. Again, 3 of them, 1 per phase, and 1 on the neutral. And then if any of those operate, they come down and hit the trip coil for a breaker. So now, interesting thing is if you're here and you start counting these up, there's 3, 4, 7, 8, 12, 16 relays in the substation that are, electromechanical relays. One of the advantages, we talked about microprocessor relays. Well, I would take those 12 down to 4. I'd have 1 relay per feeder and 1 relay doing my transformer. So size-wise, I save a lot of space. But there are a lot of advantages of the old electromechanicals. Reversible inform, you use a lot of different, in a variety of schemes. They're pretty inexpensive. You can pick one up for hundreds of dollars to, just into the, maybe if you spend $2,000, you spend a lot. Technology's been around for a long time, so protection engineers were not necessarily the people who want to jump on the new trend the fastest. Everybody understands how these things work. They're reliable, so there's still a lot in systems. before coming to Avista, I was in a consultant and did a lot of heavy industrial, and electromechanicals are still pretty prevalent there as well. So depending on the utility, the size of the utility, if you go to a PUD, then you'll still see a lot of these. So there's still quite a few of them out there. They're easy to set and test and repair, and they don't require any DCs because they self-power themselves. So here's a picture of, in this case, this is a CO9. And this is a kind of a zoom in of its nameplate. We look here, this is, we can see it's a Westinghouse. So if we look, Westinghouse, well, we all know who he was, and that's been a long, long time ago. So these have been around for a long time. ABB bought Westinghouse. So now if you buy a brand new one, you would buy an ABB CO relay. But they're still Westinghouse. I took this actually off somebody selling this particular relay. So you could go out and actually buy it. So it shows you it's a 60 hertz relay. It's a 1 to 12 amp secondary. There's an indicating circuit that's 0.2 to 2 amps. And it's a CO9. Here's the instruction manual, and here's the schematic for it. The one thing to note here, and I'll talk more about it in a little bit, is there is a stationary contactor right here. So this is the best picture I had, so I thought I'd go ahead and identify where that was at. So if we look at, we went from the 1 line to looking at a 3 line, then, here we have our bus. In this case, we actually had some reactors to lower fault current. And when you talk protection, you have to talk about a protective system. So, a lot of people think when you think protection, it's just the relay. Well, if the relay operates and there's no DC, then I can't energize the trip coil. So that's no good. So, the DC system is actually part of the protective system. The relay is part of the protective system. If the relay operates, its contact closes, I energize the trip coil, but the breaker mechanically fails, then I can't clear the fault either. So, there's the relay, the DC circuit, the breaker itself, and then this, the relay's basing its decision. In this case, since this is just an overcurrent relay, it's basing its decision off my CTs. So there's numerous things that are part of a protection system. And if you get into the bulk electric system, NERC actually has definitions of, you Google NERC's glossary of terms and look up a protective system, they'll tell you everything that's incorporated. Because if there's communications, it gets included as well. So a number of things that go into it. But, if we look here, we've got, any particular phase. We follow this up. Here's my A phase. So here's my A phase relay. It goes through terminals 9 and 8 on the CO9 relay. So it goes through both the phase or the time over current and the instantaneous. It comes over here, goes through a meter. And then remember back from the symmetrical components portion of the class, if I sum my 3 phases together, what do I get? I sum A, B, and C, and they're balanced. How much current flows in my ground?
0.
Right. So typically there's 0 current flowing back to here. But I do put a ground relay there. It's normally going to be measuring 0 for balanced 3-phase faults. These relays have to be set above load. I can set this one pretty sensitive because I don't have to worry about load. So if any of these relays operate, this is the 3 line and the AC portion of it. If they operate, we'll say that there is a fault. So in that case, then my CO would operate. So here we got plus and minus 48 volts. So if it's an A phase to ground fault, if we put a fault, down here somewhere, then my DC, the relay closes its contact when it times out. At that point, current's going to flow, come down through here, energize my trip coil, and then I'll open my breaker. Because normally when the breaker is closed, that 52A is closed. So that contact is there so that when the breaker trips, I de-energize the trip coil so that I don't burn that trip coil up. Once the breaker's tripped, there's no reason for holding that circuit in, right? Does that make sense?
Yes.
Okay. So if you actually look at one of these relays, they're pretty ingenious. The people who used to design them, they are electromagnetic devices. So I always give the people who design these old electromechanical relays a lot of credit, because I don't know about you, but Fields and Waves was probably one of the hardest classes I took in college. I probably struggled through that class as much as any. And these people did, design complex, devices off of understanding all the fields and waves and magnetics. So I have to give them some credit that they knew what they were doing. So if you actually looked at the relay, it's at kind of an E shape. Let me switch back to my pointer. So you've kind of got this E shape laminated disc. And depending on whether it's a CO11 or a CO5, will depend on, does it have both of these outer legs or just the one? So if it's a CO5 or 9, it doesn't have this right curve. So, and here's the disc that you typically see. And I can share this with everybody later, but so when we talk about the tap, it's really what you're doing. You're tapping the transformer in the relay. So, and what it's doing is it's creating an amp turn ratio within the relay to cause it to operate. So as kind of talked about last Saturday, we've got this little screw right here, and you just unscrew it, and it can go in any of these holes. So that becomes your pickup value. So that's pickup in secondary. So whatever, take your current transformer ratio, multiply whatever your pickup is time, that's how much it's set in primary amps. There's also this spiral, it's a real thin piece of copper wire. And what it's actually used for is it brings DC up to this contact right here. So this is a movable contact. And it also provides some resistance. So the interesting thing is a lot of that has the effect of whether you're on the unsaturated side or the saturated side of the relay. And if you plot 3 different relays, here's a C11 with a time dial, with a little bit different values, then you can see eventually they do cross. And that's once they hit that saturated region, that's what actually causes them to cross. So typically this disc is just flat, smooth. I'm gonna say it was brought up the last class, and I can't remember if it was who asked about it, but I have seen this have some bumps in it. I haven't been able to find anybody that knows why some of them were manufactured that way. But this is a lot more common, as it's just a smooth disc, because all you're doing is inducing a voltage on it and then getting circulating current and creating a torque. So this is the central rod that goes through it, and the disc is attached to it. Here's my movable contact. And then we have the time dial. I'm thinking of it. Yeah. So the time dial adjusts what position this movable contact is in. The lower the number, the closer this movable contact is to the stationary contact. The higher the number, the farther this movable contact is away from the stationary contact. So if we exceed a 51 element pickup, what's going to happen is through the transformer, we're going to induce a torque in this disc, and it's going to turn. Which will then start moving this time dial, this adjustable movable contact. It will start rotating around. And the relay is basically at that point, we call it its timing. So it's over its pickup, it's monitoring the current, yep. When it comes around, if it gets to its operating curve, my movable and stationary contacts come in contact with each other. Again, this copper is connected to it. That completes my DC circuit, and I energize my trip coil. So there is a dampening magnet, and I won't, some of this I don't want to go over too much. It's more if you want to dig further into it. Like I said, kind of took this from a internal presentations that we do, which is more for our technicians and engineers to understand more about the device. So there is a keeper on the other side of the disk, and that's really just a return path for the flux. As we create a field, and it can either come down this way on the left side or the right side. One of the things that had come up, we can go back and look at one of the. It's probably worth pointing out. Let me. We look here. One thing to notice is this particular relay doesn't have an instantaneous element. So the instantaneous element's normally here, and here's my target. Again, the target and seal in, they're DC operated, and it provides a visual indication of the relay operating, and it seals in. So this is actually out of the instruction manual. You can see here's my induction disk. So this is my 51. Here's my instantaneous element. I can connect to between terminals 8 and 9 for my current. The interesting thing of these cases is when you open the switch on the front, it automatically shorts these two together. Because one of the things you absolutely do not want to do is open circuit a CT while there's primary current flowing in it. If that happens, you can end up with voltages will significantly increase really fast, and the insulation won't be able to sustain an arc. So you can actually draw an arc across it. So most relays, you may go out and see test switches underneath them, or there'll be some kind of test switch built in, and what that does, the voltages and inputs and outputs, I can just open a switch and isolate the relay. Currents, almost universally that I've ever seen, have a special contact so that when you open it, it shorts on the other side of the block. And that's just for safety. So you can see, 8 and 9 here is for that. And then if these operate, then they come over here and close either my instantaneous or my seal ends. And then this can become, if I go terminals 1 to 2, then I take that into my DC circuit. And if you look back at the first drawings that we talked about, you'll find those same terminals. So the one other thing that a lot of them have is a target seal-in, and really so they're either 0.2 or 2 amp devices. It depends on what voltage that you're using them at typically, and which one you want to use. So, and what it does is when the relay operates, a little flag gets dropped. And when you walk up and look at the case, you can see this flag sitting there. It tells you, hey, I had an A to ground, my A relay and my ground relay both are showing flags. So therefore, I know what happened. If the relay has a 50 element, which that first picture didn't, then it's going to be a coil that looks like this. And where I was talking last week about there's a screw in the top, and it's pretty simple. So really, this is just a coil that we pass current through, and it's a plunger type device. So a technician will adjust this screw until he gets the right amount of current to operate it that he wants. Again, it has a hinged armature, so it's a plunger type device. When it operates, it moves and closes a contact, and again, completes your trip circuit, and it drops a flag. So again, they are electromagnetic devices, so they, produce a flux and an eddy currents induced on the rotor, or there are eddy currents induced on the rotor by those fluxes, which then causes a torque, which then causes your disc to move. So if you want to look at what the phasors of them look like, this is, what the phasors of them again look like. So if you want to dig into it more. So thought it just as interesting to talk about some of the uses of them. So, when we're doing distribution protection, and we'll kind of focus on that because that's been the focus of this class, what are we, trying to accomplish? So our goals is to protect people, whether that's, company personnel or the public, and equipment through properly applying overcurrent protective devices. Now, I'll caveat that protecting people part, because even if an instantaneous element operates, a typical breaker is anywhere between, depending on the vintage, a modern gas breaker is, I've seen a lot of them operate at about 2.5 cycle, even though they're listed at 3, and you can go all the way back to old oil circuit breakers, and some of them are as slow as 10 cycles. So if you have someone with 1,000 amps flowing through them for that long, chances are they may not make it anyways. So I always caveat to protecting people. We do the best we can, but there's no guarantee that if somebody comes in contact with a live circuit, that the breaker operating time alone can be enough to kill somebody. So the way we do that, we trip circuit breakers and circuit switchers, or fuses, and we use a thing called a TCC. So it's a time current coordination curve, and we use it to look at coordination between 51 elements. This is kind of what a TCC looks like for those of you who've never seen one. So on the x-axis, it's a log scale. So on the x-axis, we've got amps. Sometimes you'll see this as multiples of pickup instead of amps. But amps is a little more common. And then along the y-axis, we've got seconds. So again, in a log scale. So depending on what vintage or relay you're dealing with, the shape of the curve is actually different. Now, if you look at electromechanicals, like a CO11 is a very inverse relay. All these, if we'll pull out a CO instruction manual, extremely inverse, very inverse, moderate, and short time, all are designated by CO dash some number. In microprocessor relays, they just gave them the names: extremely inverse, very inverse. So we look at this, all these relays have the exact same pickup. But they have a different time dial setting. So just to separate them, but you can also see the difference in the shape of the curve. So the extremely inverse is the steepest one here, and the short time inverse is the bottom. But we tend to use extremely inverse the most because it coordinates really well with fuses. Again, a little bit of discussion of what a pickup is. Again, it's the current which the relay will operate a trip to breaker. Another term for that was, the tap. It's expressed in terms of CT ratio. So if we have a relay with a CTR of 120 and it's tapped at 4, then it's 480 amp primary. The time dial again is at what time delay the relay operates the trip to breaker. The larger time dial, the slower it is. Old term for that's the lever. important thing to note is, and I think I commented some in the chat about this, is you can't coordinate instantaneous elements. By definition, an instantaneous element is an element that operates with no intended time delay. So if we look here, these two, this number here and this number here, they're pointing to two different pickups, but the lines lay right on top of one another. So if I have a 3000 amp fault, I come in contact with both lines at the exact same time. So there's no coordination between them. So you really can't coordinate instantaneous elements. And the way you read a TCC is you pick a value, say 3000 amps. We follow it up. Well, I'd hit my instantaneous first. And I think it was Michael that said, they have those turned on first and then they turn them off. So we do in my utility, we do what's called fuse saving. So for an initial fault, we hit the instantaneous element and we trip. Then we reclose. At that point, we turn these off. So now it's not there. So the next operation, it should be by the fuse. If for some reason a fuse failed or it didn't interrupt the fault, we would go up and start running into the protective curves. In this case, we've got a fuse, we've got the station breaker, and then the transformer relays. So if you follow, the way you read these is, you just follow them straight up. Pick what your fault current is, follow it up, and it will tell you exactly how the devices operate. This diagonal line here is the conductor damage curve. So we're making sure that we're protecting the conductor that's out there. And this, again, I think come up at some in discussion. A lot of utilities practice the protection is there for faults, not to, we're there to protect this conductor from a fault. We're not there to keep you from overloading the conductor and burning it down. So,
Kevin,
can
I ask a question here?
Yeah.
What I understood from here, from the discussion board, also part of it, that there is no coordination for the instantaneous element relays. I'm not fully understanding that part, that if there is no coordination for 51 for the instantaneous element, then why we are using them, or I would say, and we also studied that it worked based on the impedance. The farthest we go, we have the higher the impedance. So the flow of current will be different at different points of the line or of the circuit down the road if you're getting away from the source. So can we still coordinate, have a coordination using instantaneous element with the impedance change down the line, or we can't have any coordination literally with instantaneous element, and why we are using it then?
So that's a good question. There's a number of different uses for them. Like I said, one of ours is a fuse saving scheme. So even if a fault is on a lateral past a fuse, well, every time we have to go, if that fuse blows, that I've got, I've lost customers. So now I've got to have a crew go find the location. Hopefully they've got that fuse size on their truck, and then replace the fuse. If they don't have the fuse size on the truck, then they have to go back to the main office, get that fuse, drive back out to the site, and put a fuse in. Well, for CADI, SAFE, all of our reliability indices that our utilities are measured for, the longer someone's out, the worse off, right? Those numbers get worse. So, and there's just the cost of the fuse. Those can be, depending on what size of fuse it is, they can be a couple $100. So by doing a fuse saving scheme, yes, you're blinking, there's going to be a trip reclose, and depending on the philosophy of the utility, and it can be, depending on where the fault's at, it can be at the station breaker and the recloser. And I can show you a figure here in a little bit, and we'll talk about that. You may blink both, but it's going to be a blink. You're going to open, wait. Say in our case, we do a half second. For our first reclose, we do a half second. So we open up, close right back in. Customers see their lights flicker is about all they see. Half second your main brain doesn't process that fast. So we see your lights kind of flicker once, you go, oh, what was that? That's a trip reclose. So anytime you see it, I always tell my friends who live here. So our philosophy is, and different utilities have different practices. We do one fast and one slow reclose. So the first operations is by our 50 elements. We'll trip. Again, we're trying to save this fuse, make sure that we don't have to replace it. So we'll trip, wait half a second, reclose it back in, then we turn these off. At that point, we're just using the 51 elements to coordinate and say, each one's backing, ideally, we don't get up into the transformer because that's bad. That means I've got, the fuse somehow failed, my relay, my substation breaker failed, and now I'm, getting up into the transformer protection to back this thing up. So ideally not doing that. Another thing that you're starting to see is, and I mentioned it, I think last weekend. So me and a coworker, wildfires are becoming a bigger issue for a lot of people at utilities. I don't know about your utility, but for us, it's becoming a significant concern. So we've, in the recent last year, or about a year and a half, we started a program that, we're trying to mitigate that fault as fast as possible. So instantaneous elements are great for, we're trying to minimize how much energy goes, if a conductor falls down on the ground, how quickly do we detect that and how quickly can we clear it so that we put less energy into that fault point and are less likely to start a fire. So a lot of utilities are going back to using 50 elements to speed up fire hazards. Now, you only turn those on during certain periods because, again, it has a significant impact on the reliability of the distribution feeder.
So is it mostly used then preferred to use only on the distribution part, not on the transmission, right?
So you don't typically use, if we go back to that first slide, or one of those first slides, only time you can use an overcurrent like this typically is for transmission if it's radial.
Okay,
so
sounds
a
good.
radial transmission line is the same as a distribution feeder, right? But generally most distribution or most transmissions operated non-radial.
Right, impedance. And I got it. I think you answered my question. Thanks, Kevin.
No problem. So just, if you ever want to have a lot of fun and, spend some time in protection, interesting thing here is this is kind of showing the effect of the time dial on the pickup. Here we had the same time dial 9, and it goes anywhere from a pickup of 320 amps to a pickup of 900 amps. Well, if you look at this and go, Kevin, curve 1, it's way over here. It stops here. Well, if you draw, what they do is they draw a dashed line up. Well, this line, number 1, would come all the way up to 960. So it come up just to here. And the reason they do that is, again, this is an electromechanical device. So the manufacturer only guarantees that it's going to operate at about 120, 125% of pickup. Before that disc could start turning, but they're not going to guarantee you that it's going to operate at a specific time. So that's why you see curves, even though this curve 1 actually goes all the way up to 960, it really starts over here closer to, almost 1500. So it's anywhere from about 1.25 to 1.5 is where they actually start the curves. That's only for electromechanicals. For microprocessors, I can promise you at 101%, it will start because it's mathematical. It's not an electromagnetic device, right? As long as your CTs are accurately measuring, then the device will operate at 100%. So it'll be slow, and you're going to be up here in hundreds of seconds, but it will operate. So you can see by adjusting the pickup, I can move the curve left or right. time dial, again, here we got the same pickup, but we go from a time dial 2 to a time dial 15. For 2's here, 15's up here. So time dial, I move the curve up and down. Pickup, I move the curve left and right. So we talked about, a lot of advantages of microprocessor relays. There's all kinds of advantages. I don't think I mentioned it yet. This curve right here is actually my transformer damage curve. So this is what a transformer damage curve looks like. Depending on the class of transformer, it's going to have this knee that comes out of it. So nice thing of microprocessor relays is we get phase elements, we get ground elements. There's a difference between N and G. N is actually measured, and this depends on the manufacturer. In some manufacturers, the N is for measured ground current, and the G is for calculated ground current. So calculating 3I0, so IA plus IB plus IC, that gives me 51G. And then I get negative sequence. You didn't see a negative sequence in electromechanical a whole lot just because it was hard to wire up. So it was just not, people didn't use it that much. But with the getting microprocessor relays, it became pretty easy to do because it's built into the same box. So I can do all these different functions where you remember back in the electromechanical where I showed you, I had 3 51Ps and 1 ground. Well, now I've got a single 51P that operates off any one phase. I got grounds and I get a negative sequence, and most manufacturers actually give you multiple levels of these. I may have up to 4 or 5 51Ps, so I can use them for different things. So a lot of advantages of microprocessor relays. On top of, and I mentioned, being able to change setting groups is another big benefit. So this kind of goes back to our discussion of some of the other benefits of microprocessor relays, and Dr. Gers had brought up what are some of the benefits, especially when changing the configuration. If you look, most utilities up until I'm gonna say 10 years ago operated their distribution feeders radially. You might have had a feeder breaker and a switch, and the only thing protecting the feeder was the feeder breaker. You might have had a feeder with a feeder breaker and a mainline recloser to break the feeder up. But starting about 2010, at least at Avista, when we did the smart grid, the thing that we did was we made it in a lot of locations where it made sense to do it, especially in urban, semi-urban, not New York City urban, but Spokane, which is a city of about 500,000. So a decent sized city. We had a lot of distribution feeders that were near one another, but weren't, there was no way to connect them. Well, for reliability, it makes sense to connect them, right? If I have a fault somewhere, I can transfer some load and pick it up off the other substation while I isolate the fault. So we started tying with normally open ties a lot of our feeders together. So as I was saying, one of the advantages is if I had a fault that was here, then I could open my or I was even doing I was trying to maintain my feeder breaker. I can open this breaker, close this switch, and I can carry all the load from the other substation. Now that affected the fact that normally these two feeders, this was a forward direction. It was flowing from the feeder breaker to the recloser. This feeder was flowing from the feeder breaker to the normally open as well through its recloser. So both those reclosers, if I put a fault past them, if I put a fault right there, if I put a fault here, and this breaker is going to open, right? Nothing's going to happen on the other feeder. But again, if I had this feeder breaker out, I can close this switch, and now this, the two feeders are tied together. And the big change is we started using directional elements, where in traditional feeders we had no use for directionality. Now directionality becomes important, and we use it to coordinate the number of recloses. So if we're in this configuration and we have a fault here, then both devices, we're going to trip. So these, in most instances, these two devices are actually set either really close to one another or sometimes almost identical settings. So for a fault here, both of them are going to see it and trip, and then they'll both reclose. If the fault's permanent, then they're both going to trip again. The difference here is this one trips and locks out at that point. So I got one reclose trying to restore this section. But this recloser goes through another reclose to pick up everything except for this breaker. So at this point, I've locked out this breaker. Now I'm picking everything back up to this midline recloser, and I've isolated the fault to this bus section. So that's the reason we use the forward reverse, is because generally a lot of our applications, these two midline reclosers are set almost identical to one another. We can't really coordinate them. So,
Kevin, if the fault is on the other side, if the situation is opposite, then if you're making this this right side one midline recloser, you're putting a lockout in that one and not the other one, then I don't know how it's gonna work. If you can you explain the situation if the fault occurs on the left side, on the other end?
Oh, so you're saying here? Are we talking about a fault right there?
No, further next to the feeder breaker on the left. Like next to the switch on the left, and just
yeah. Let me erase this, and so you're talking of the feeder breaker here?
Yes.
Between the feeder and the switch?
Yes.
Oh, in that case, so if we were to have a fault there, then I only have a source from one end, right? This feeder breaker's open, so I don't have a source at this end. So if I have this
source. Okay, so I thought, okay, now I understand. So we have only source on this end, so we don't have source on the other end?
Well, you do.
Okay,
but in this application, we're open right here, right?
Yes.
That's what the green is open.
Okay, so if it's closed, if everything is closed and the fault is on the left side that you have already shown with your markup, if the fault is there.
The only time we have this closed with being fed from both ends is during switching.
Oh,
so they would, because normally what would happen is, because we don't want to drop load, is they will they may come, they'll come here, close this switch, and then open this breaker.
Okay.
So the time that takes them to close the switch and then open the breaker is the only time that you're technically a non-radial feed.
I see.
And the the probability of a fault during that time fairly low. Not that it couldn't happen, but we really haven't seen too many of those. Especially since our system operators have control of the switch and the breakers, so they can remotely operate all this. So they click and it's all on one screen. So it's the time that it takes him to click to tell one device to close. He gets the close indication. He and then clicks open on the other one, and then he gets an open indication. So you're 5 seconds, 10 seconds.
Yeah, no,
at most, it's not a significant amount of time.
Right. So are they going to keep this one as a normally open all the time, or they can shift it? They can make the other end as a normally open as well.
They can use they can do the same thing. They can open, they can open in between any device. And I think it was Michael was talking about, one of the other nice things is we actually put in a protective function we have 50, I'm gonna call it 50 hotline hold on our switches, as they are actually, or our switches that we installed are actually Vipers. So they're a recloser that's dumbed down. Normally, it has no protective function, except for when someone is working. So if I've got a crew working in this area, you're going to love my stick figure here. There, he's even got his hard hat on, so he's working safely. If I got a crew working between the switch and the midline recloser, I know that somebody's in this area and there's a risk of them coming in contact. So what they can do is they can take a hotline hold at the switch, which then turns on instantaneous elements. But those instantaneous elements only reach to the recloser. So what's that do? It gives him added protection. We turn on that, when we do that, the hotline hold, it does two things. It turns on a 50 and I'm gonna say not 79. Yeah, so we turn off the instantaneous element and we turn on the instantaneous and we turn off reclosing. So which a switch normally doesn't have reclosing anyways, but the same functionality is built into all of our midlines. They can take a hotline hold in between two midlines. Again, this tie point, some of them have some of them are actually Vipers, some of them are a different manufacturer that we can't do that with. So they can take it either between the two reclosers or between a recloser and any switch.
Okay, so if let's suppose if they're shifting their normally open breaker from right towards the left, if they're making the left one as a normally open, so do you think they will have to shift the relay like lockout condition from right to left also, or the forward reverse will be opposite also?
Well, it's just naturally what direction does the fault current flow. So there's nothing changing other than the relay is, to do this, the forward and reverse, the relay has to have a PT. And at that point, it's comparing what's the angle between my voltage and my current, knowing that a fault is typically going to be, voltage is going to lead current by about 90 degrees. So it's looking at that phase angle between the two to say, is the fault in front of me or behind me? So that's all logic in the relay.
And you mentioned that there will be one recloser shot for the right one, for the left one, I guess, or for the right one, and two for the left. Shouldn't it be changed?
Yep. So yeah, if we were feeding from the right hand side to the left, these two would automatically swap.
Okay. Yep.
So because fault over here, then let me turn my laser back on. Now, yeah, you just basically take everything and flip it around, but it operates the exact same.
But we have to change the recloser setting. Then we have to make one shot here and the two shots.
Nope. The relays automatically do it because they're just using is the fault in front of me or behind me.
Oh, okay.
So there's no setting changes. It's just the only change is now the relay. We had to add PTs to our reclosers.
Okay.
So which is good because that gives us more data, voltage wise, monitoring. It's more data coming back to our SCADA system of how is the distribution feeder really? What is it's another voltage point out on our feeder that we can look at for a lot of different reasons. So we can bring that back into our PI system so our operations engineers can see, what's their voltage look like for customers. So there's a lot of advantages to it. The other thing is it allows us to do directionality.
Very good.
We're not changing settings. It's the relays just automatically determine is it in front of me or behind me and change the way they behave.
I got it. I was just like focusing on 5051, but now I realize when you mentioned about the voltage reference, now it comes to directionality. It can sense. Thanks, Kevin. Yeah. Appreciate it.
So some kind of another example. So this is a little more complex system. So here we've got a substation, two feeders coming out of it. And this feeder goes up. In this case, we've got three reclosers going off in three different sections. Normal power flow is Z01 and down to this normally open point. On feeder 2, I come out, I got, Z03 forward and Z02 coming over here again to this open point. So what we can do is when I close this normally open tie, because I'm doing, again, say I'm working on my substation feeder breaker, I can't coordinate a lot of different devices. So if we look, here I've got a forward device, and here's already a forward device. When I close that switch, now I've got a forward device. This would be a reverse device and then a forward device. Well, we talked about the number of recloses being different. So what we do is when we configure this, they can actually, our system operators can switch this device to switch settings. So again, it allows them to apply a hotline hold in between these two devices. But other than that, now I'm just coordinating Z01R with Z03R. So microprocessors have a lot of possibilities. Once you start putting these, smart midline reclosers out there, you can do lots of cool things with them. And what allowed us to do our dry land functionality for wildfire mitigation, all was a result of what we did in 2010 of having all these smart midline reclosers out there. Over the last year, we did, we identified for us the requirement was it had to be a midline recloser that was a microprocessor based, and it had to have communications to us. We quickly identified, and last year we're able to do just over 100 devices, because we had a number of devices already out on our system that met that criteria. So, it's actually a 10-year program to mitigate all the fire risks on our system, but we were able to make a huge, jump from 0 to 100 devices in less than a year. And it was all because we already had microprocessor-based reclosers out on our feeders. No, the other thing I talked about was, if you have slapping conductors. So if you have a fault past, we'll just go back to the normal one. I've got my station breaker back here. Well, if I have a fault past Z01R here on this lateral, you may have Z01R and the station breaker both trip. And then we've had instances where they both tripped, they both reclosed. Let me go back to, yeah. So they both tripped, they both reclosed, and then the station breaker tripped the lockout. And our system operators, area engineers, it's always brought to us and, hey, you guys miscoordinated. And what we were able to determine was this was fault 1. Then they would have a subsequent fault from slapping conductors somewhere in between the midline and the breaker, station breaker. And the way we can do that, we talked about fault current goes down as you go farther out on the distribution feeder, right? Because the amount of impedance. Well, this fault was 1,000 amps. The subsequent faults that actually locked out the feeder breaker were 5,000 amps, which means it was a totally separate fault and a whole lot closer to the substation. I think that's all I've got. You guys got any more questions, comments, snide remarks?
Kevin, I don't know if I can ask. I have a couple questions since you're on the call, but I don't know if it's the right time to ask or not. Maybe you can discuss later also. It's related to the knee plan. If I can show you something here, but I don't know.
Can we do those offline? So
Yeah.
so if you want to, if you don't mind, can it wait till tomorrow?
Yeah, that's fine. That's fine.
Okay. But say I should be home most of the day tomorrow. So just text me or give me a call and we can talk.
All right, very good, very good. I don't know if I have your contact or it's there on the.
I'm about to say on the syllabus, you've got my cell phone number and I think my work number.
Okay. Thank you, Kevin.
No problem. All right. Well, if nobody's got any questions, appreciate you listening in. Hopefully you learned something.
All right. Thank you.
All right, everybody. Well, hope you have
Right.
a good weekend, and as you work on your final, if you got any questions, let me know.
Okay.
Bye, everybody.
Okay. Bye.
Bye. We can all. Thanks. Bye.